Trigonometry, presented by Jamie Smith. Given that most of the content in terms of theory for trigonometry has already been taught for GCSE and A-level, then we are going to go straight into some examples applying that theory in problem-solving situations. Express the perpendicular height h of triangle ABC in terms of the angle C. Hence or otherwise prove that the triangle area equals half AB sine C. Pause the video, have a go at this yourself, and then when you're ready, press play to see the solution. So the question tells me to express the perpendicular height h of the triangle ABC in terms of the angle C. I'm going to do this using standard GCSE trigonometric ratios, SOHCAHTOA. In particular, I'm going to focus on sine because sine's in that triangle area formula. So sine, remember, is the opposite over the hypotenuse. So we're going to write out sine of C equals that opposite, which is h, over the hypotenuse, which is A. I realise it's a little bit confusing using the h as the opposite there, but we just have to deal with that. So multiplying both sides by A, I can rewrite this as h equals A sine C. Now it tells us to prove the triangle area equals to half AB sine C. So triangle area, as we should all know, is equal to half the base times the height. In this case, we've got the height is A sine C. So if I multiply that together, we get half B times A sine C, which of course I can then tidy up and write in more conventional form, half AB sine C. Okay, this example's a little bit trickier, but hopefully you can have a go. So in example 2, it tells us to express the perpendicular height h of triangle ABC in terms of the remaining sides of the right angled triangle containing A. It says then to repeat this with a right angled triangle containing angle B. Hence or otherwise prove the cosine rule. So what we're talking about there is that right angled triangle containing angle A is this one that I'm highlighting there. So again, pause the video, have a go at this for yourself, and then when you're ready, press play and we'll have a look at the solution. Again, in this question, we're going to start off by following the guidance. It says to write the perpendicular height h in terms of the remaining sides of the right angled triangle containing angle A. So what we're looking at here is this right angle triangle here. Now, notice it says to write it in terms of the remaining sides. So what we're talking about using here is Pythagoras' theorem. And again, we were taught that at GCSE. So we're just going to use that the hypotenuse, which is in this case B squared, is equal to the other two sides. So that's going to be x squared plus h squared summed together. And that's all that guidance was saying, was express that perpendicular height in terms of those other two terms. Now, at the moment, strictly we haven't done this because h squared is not the subject to the formula. So let's rearrange and rewrite this as h squared equals x squared, b squared minus x squared. Let's correct that and put in b squared minus x squared. Now, I'm not going to fully rearrange it in terms of h. I'm just going to leave it in terms of h squared at the moment. You'll see why in a moment. Okay, so next it says repeat this with a right angled triangle containing B. So you'll notice we've got this other right angled triangle here, which I'm now highlighting, contains angle B. So I'm going to do exactly the same, and we're going to do the hypotenuse, which again is this time A squared, is equal to the other two sides. So I've got h squared, and the remaining side, well, this length that's unmarked, that's the difference between C and X. So we're just going to label that as C minus X. So I get plus C minus X squared. And again, if I make h squared the subject, we get h squared minus C minus X all squared. Okay, so we've done the part of the question that involves the guidance. Let's have a look now at the last part, which says hence or otherwise prove the cosine rule. So I've got these two expressions for the perpendicular height h in terms of the other sides. So what I'm going to do is I'm just going to eliminate that h squared, because we know that the cosine rule contains only the sides A, B, C, and then cosine of an angle. So let's eliminate the h squared, and I can do that just by substituting h squared from one equation into the other. So what I get in that case is I can have a squared minus c minus x squared equals b squared minus x squared. Okay, so I'm going to rearrange and I'm going to make a the subject, because this is starting to look a little bit more like the cosine rule now. So we're going to have a squared equals b squared minus x squared plus c minus x squared. Okay, so it's not quite looking right at the moment, but we'll expand the bracket c minus x squared and see what happens. So if I expand that, then what we lead to is I get a squared equals b squared minus x squared plus c squared, and then get minus 2cx and plus x squared. And this simplifies to give me a squared equals b squared plus c squared minus 2cx. Now this is incredibly close to the cosine rule now, because I've got that bit which looks like the Pythagorean formula, a squared equals b squared plus c squared, and then I've got that little adjustment at the end, which is usually minus 2bc cos a. So what we have a bit of a problem with here is this x term. So I need to get rid of that x term, and the way I'm going to do this is that I know that the cosine rule for this particular format, when it's a squared equals, must contain cos a. So I'm going to write the term x in terms of cos a. Now cos, soka, toa, adjacent over hypotenuse. So I'm going to get cos a equals adjacent, which is x, over hypotenuse, which is b. And this rearranges to give me b cos a equals x. And finally, if I substitute this into this expression that I've got, a squared equals b squared plus c squared, I replace the x, so I can then write this as 2 minus 2b, which comes from the b cos a, c, and then cos of a. And there you have it. We've proved the cosine rule. Example 3 says pentagon ABCDE has side length 2 centimeters. Show that tan 15 degrees is equal to 2 minus root 3. Have a go at the question. Pause the video, have a go at the question, and when you're ready, press play to see the solution. This question is telling me to find an expression for tan 15 degrees, which immediately tells me I want to use GCSE trigonometric ratios, SOHCAHTOA, TOA, in particular TOA, because we're focusing on tan. Now immediately I notice that there's no right angle triangles, so I'm going to start by breaking up this diagram to try and get a right angle triangle. Now that first line actually breaks this into a square and an equilateral triangle, not a right angle triangle. So I'm going to extend this to create a right angle triangle. Now, if I start labelling some of the sides, I know all of these sides with the line are 2. So I know that this here is a 1, I know this is a 2. Okay, so I'm just focusing on the triangles for the time being. If I've taken an equilateral triangle, what I've actually done there is I've split this, so we've got a 60-degree angle down at E and two 30-degree angles up at D. Still wondering how I'm going to find this 15-degree angle though. Now if I've got a 30-degree angle, I could cut a 30-degree angle in two to get 15 degrees. Now that's going to be quite tricky, because what triangle are we actually going to form at this point? Well, this is a key part of the question, and it's a little bit tricky, this one, because if I focus on angle C for a second, and just label this could be in a triangle where if I connect the side, or the corner should I say, D and B together. Now, why would I want to do that? Well, notice that the triangle CBD has two sides that are both 2. So this is an isosceles triangle. So that means that these two angles at the top here are going to be the same. Now, I know at angle C, that's a 90-degree angle plus a 60-degree angle. So that's 150 degrees. And that means that we've got 30 remaining to split between these other two angles. So I get 15 degrees and 15 degrees. So now I've got that 15-degree angle, but I still haven't got it in a right-angled triangle. And so what I do is I'm just going to extend, and I've got this other 15-degree angle here. Now I've got this small right-angled triangle that I'll just use a little highlighter pen to do it. Here. I've got this small right-angled triangle, but I don't know the length of the hypotenuse, and I don't know any of the sides of that triangle. There's one I can find, but there's not going to be enough information there. So what I'm going to actually do is I'm going to extend this line down to the bottom here so that I get this right-angled triangle. I'll label it in a second. Apologies, that's the wrong one. Let's get the highlighter pen. So I get this right-angled triangle here. And I'll label the bottom bit just F, just so we're clear. So I've got the right-angled triangle BDF. Now actually I know one of the sides. That's BF, that's 1. I've just split that square in half. And actually I know part of that perpendicular height because I know it's a length 2. So can I find this little bit here? And the answer is yes. If I just take to the side a second that triangle which we got, 60, 30, it's got a base of 1, hypotenuse of 2. What we can do is we can use Pythagoras to call this x. That x squared is going to be equal to the 2 squared minus the 1 squared. So we're going to get x equals root 3. So this red side is root 3. And now what I know is that the side FD is equal to 2 plus root 3. Okay, so I'm there now. I've got a right-angled triangle that involves the angle 15 degrees. I know the opposite side FB, which is 1. That's this one down here. I know the adjacent side, which is DF, which is 2 plus root 3. So I can now write out that tan 15 degrees equals the opposite, which is 1, over 2 plus root 3. Now, unfortunately, we're not quite there yet. I need to take this expression 2 plus root 3 and rationalise it by multiplying top and bottom by 2 minus root 3. So in the numerator I get 2 minus root 3. In the denominator I'll get 2 squared minus root 3 squared. And that's of course using a plus b times a minus b equals a squared plus b squared. So in the denominator what we get is 2 minus root 3 over 4 minus 3. And so what we get left with in that case is 4 take away 3 is 1. So we get tan 15 degrees equals 2 minus root 3 as the question asked. Example 4 says the diagram shows the unit circle centre the origin and radius 1. For any angle theta with theta between 0 and 360 degrees, let P be such that the line segment OP makes an angle of theta turning anti-clockwise with the positive direction of the x-axis. In these circumstances, the definitions of cos and sine are as follows. Cos x is the x-coordinate of P, and sine x is the y coordinate of P. Essentially, this is saying that no matter what the angle theta makes with that x-axis, the point P will be cos of that angle, sine of that angle, as the coordinates x and y. Part A asks us to explain why, when theta is acute, these definitions agree with the familiar ones for a right-angled triangle. So we want to explain why is the x-coordinate cos 20 and the y-coordinate sine 20 for an acute angle. Pause the video and see if you can explain this before pressing play to see the answer. Okay, so really all we're talking about here is what happens when theta is less than 90 degrees. And we have in the diagram at this point, theta less than 90 degrees. So we've got this 20 degrees. And if I was to change this into a right angled triangle, this length across the bottom, our base, would represent our x-coordinate, and this length, which represents our perpendicular height, would represent our y-coordinate. And so with our familiar definitions for a right angled triangle, the only definitions we know for the right angled triangle involve Pythagoras and trigonometry. So as this involves an angle, we must be talking about trigonometry. I want to see, can I represent x coordinate as cos 20? Now, key to this is just to remember that this is the unit circle, so this hypotenuse is 1. And so if I say, try to express x in terms of a trigonometric ratio, x is adjacent to 20 degrees, so we get, and we're going to use the hypotenuse, which is 1, so we're going to use the cos trigonometric ratio. So I get cos 20 is equal to the adjacent, which is x, over the hypotenuse, which is 1. So in other words, x equals cos 20 as stated in our question information. If I do the same for y in this case, y's relationship with the angle 20 degrees is opposite. Again, I will use a hypotenuse, so we're going to use opposite and hypotenuse sine. So we get sine 20 degrees is equal to y over the hypotenuse, which is 1. So we get sine 20 equals y. And so you can see here that the definitions that we've been provided in the question agree with our familiar ones, because all we've got is a standard right angled triangle. Part B asks us to explain why cos squared theta plus sine squared theta equals 1, having remarked on the notation used. Pause the video and have a go at this explanation yourself, and when you're ready, unpause to see the solution. So the first thing I'm going to do in this solution is I'm just going to slightly modify my diagram. Apologies if this was a little confusing for you, but I'm going to change this to just the general angle theta rather than a specific 120 degrees. And again, like in the last part, I'm going to change this into a right angled triangle. Now, again, we know this base is the x-coordinate and that height is the y-coordinate. And the base is adjacent to the angle, so I can use cos of theta equals adjacent, which is x over the hypotenuse. Hypotenuse is still 1, it's a unit circle, so the radius is 1. So I get x over 1, which is x. And I get, to find y, I do exactly the same as I did before. Sine of the angle, y is the opposite, so we're going to say y. And then over the hypotenuse, which is 1. Okay, so how do I get from here to this identity involving cos squared plus sine squared equals 1? Well, we're going to go back and use Pythagoras. Pythagoras' theorem states that the hypotenuse, 1 squared, is equal to the sum of the other two sides squared, so x squared plus y squared. Or in other words, 1 is equal to cos theta squared plus sine theta squared. And of course we know that actually the neat and tidy way to write this to avoid ambiguity is to put the squared index on the actual trigonometric function before the theta. That's just equal to 1, as we have been asked to do. Part C states that for almost all theta satisfying 0 less than theta less than 360 degrees, the ratio tan theta is defined by tan theta equals sine theta over cos theta. It says to explain why this definition agrees with a familiar one for right-angled triangles when theta is acute. Again, pause the video, have a go at this for yourself, see if you can do the explanation, and then when you're ready, unpause. So like the last example, just going to modify this to that general case and change these 20-degree angles to thetas. Again, and hopefully you're getting the hang of this now, there's going to change this into a right angled triangle. I know the angle's theta, I know that the hypotenuse is 1. We've seen a couple of times now that this base x is equal to cos theta, and this height y is equal to sine theta. Tan theta is equal to, let's just quickly, tan theta is equal to the opposite over the adjacent. So what we get here is that tan theta equals y over x. And then if we substitute in those trigonometric equivalents, I get tan theta equals sine theta over cos theta. Now, it does say for almost all theta satisfying 0 less than or equal to theta less than or equal to 360 degrees, because it's not true for all theta. And so it's a good idea to think about when is this not true. And you may have come across this when you've been doing examples, but there are times when this isn't going to be true. And they may occur at the 90 degree, 180 degree, 270 or 0 mark. So because of the x value. So here we have 0, 0. And so we get 0 divided by something is 0. That's fine, it's defined. But here we have the coordinate 0, 1. So you'd get tan theta equals 1 over 0. And we can't divide that. So it's actually undefined. So nearly all angles will work. There is another one, I'm going to leave that for yourself to find. But nearly all angles are then defined by this definition of tan theta equals x over y. The last example really gives us the background that's required to understand the cast diagram. Cast diagrams are a really useful tool for trigonometry, in particular when you're working with trigonometric ratios and problems when you don't have a calculator, such as in the UKMT or MAT and STEP papers. So it's really important you can understand where the cast diagram comes from and how to use it. What we've defined is these definitions for sine theta, cos theta and tan theta using the unit circle, which has a radius 1 and centre 0, 0. And what we was doing was we was looking at this acute angled triangle in the first quadrant where the hypotenuse was 1, the base was x and the height was y. Because what we were defining and saying is that this point on the circle is always x, y. Now what we can do, let's just label the angle theta there. What we can now do is extend this idea that we've seen in order to get definitions for trigonometric ratios of angles greater than 90 degrees. So for example, let's go for an obtuse angle. Measuring from the x-axis, so an angle between 90 and 180 degrees, is now in that second quadrant. I know that this coordinate is still going to be x, y. So how do I define this trigonometric angle? Well, what I do is actually I still create an acute right angled triangle, and I make that triangle angle with the x-axis. And now using this in trigonometric definitions, we can calculate our lengths of x and y. Similarly, if I wanted to do an angle, say, greater than 180 degrees, what we would do is we'd extend our angle round into that third quadrant. There's my angle theta. The point on the circumference is still xy. How do I calculate and identify what those values are? Well, I do exactly the same idea again. I make a right angle triangle with the x-axis, and then I can calculate those values. And we can take this idea all the way round into the fourth quadrant in exactly the same way, just taking the angle from the positive x-axis into that fourth quadrant. Here's my radius, and each one has one, that's one, that's an angle of 1. And then again, create that right angle triangle. That's an acute right angle triangle that's going to be used to calculate that x and y coordinate. Okay, so that's all we're doing. We're taking an angle from the positive x-axis and measuring anti-clockwise for any angle that we want. We can go from 0 to 360. We can extend it and go past 360. We just get the same angles again because I come round and I go back into the first quadrant and then second and third and fourth, and you keep on going round and round. You can even do it for negative angles because you just then go clockwise. So starting at the positive x-axis, work round into the fourth quadrant, into the third quadrant, etc. Now, where does the cast diagram comes from? Well, the cast diagram comes from if we look at these 4 different scenarios. When we've got our radius and our point in the first quadrant, you'll notice that the coordinate for y will be positive, and so sine theta is positive. And the coordinate for x will be positive, so that will also be positive. And then tan theta, which is x over y, will also be positive. So what we can say is that all trigonometric ratios in the first quadrant are positive. If we move to the second quadrant, we notice that in the second quadrant, we would get a positive value for y. However, because we're to the left of the y-axis, we would get a negative value for cos. And that means when I do sine divided by cos to get tan, I get a negative answer. And now you can see that the only trigonometric ratio that's positive in the sine quadrant, in the second quadrant, sorry, is sine. We can just go through all 4 quadrants. So the third quadrant, y is going to be negative because it's below the x-axis. X is going to be negative because it's to the left of the y-axis. And tan is going to be a negative over a negative. So we get a positive. And the only trigonometric ratio positive in the third quadrant is tan. And then finally, the fourth quadrant, we have that sine theta, y is below the x-axis, so it's going to be negative, and x is to the right of the y-axis, so it's going to be positive, and a negative divided by a positive will be negative, and so that we get cos. And so we get the cast diagram in the fourth quadrant. We have C, in the first quadrant we have A for all, in the second quadrant we have S for sine, and in the third quadrant we have T for tan. Actually, let's just make that a little bit clearer. Apologies if that's confused things. I'll just put tan down there and cos down there. Example 4 says to state the trigonometric ratios are 270 degrees. I'll give you a clue. Use the cast diagram. Pause the video, have a go at this for yourself, and then when you're ready, unpause and we'll have a look at the solution. Right then, let's have a look at the trigonometric ratios of 270 degrees. So here's my cast diagram. If I draw an angle of 270 degrees, what we see is that it lands exactly on the y-axis. Now this coordinate down here, remembering that this radius is a length of 1, it's 0 in the x direction and it's -1 in the y direction. So using our definition, we know that sine 270 degrees is equal to the y coordinate, which is -1. We have cos of 270 degrees is equal to the x coordinate, which is equal to 0. And finally, we have tan 270 degrees is y over x. Apologies, that's the wrong way round. Y over x is, of course, -1 over 0, which is undefined. And you can check this on your calculator, and you'll get those values for sine and cos. And when you put in tan 270, you'll get an undefined value. So this is where some of the angles that the cast diagram can be useful to help calculate without a calculator. Example 5 says to prove sine theta equals sine 180 degrees minus theta. Again, I'll give you a clue. Use the cast diagram to see if you can do this. So pause the video. Once you've had a go, unpause to see the solution. To show that sine theta is equal to sine 180 degrees minus theta, I'm going to assume that theta is acute, just to make life a little bit easier for me. And I'm going to use the cast diagram. I'm going to draw that angle in when it's acute. And so if I was to create a right angle triangle, what I know is we get that right angle triangle, x, y, and so sine theta equals 1. Now to deal with 180 degrees minus theta, what I'll do is I'll start at the y-axis now, at the x-axis on the negative x-axis, and I will go minus theta degrees. So minus theta degrees will take me clockwise. So that's where I've done. And so that means that when I measure my angle from my positive x-axis, I get 180 degrees minus theta. Now again, making that right angle triangle, the hypotenuse is still 1. This time I've got minus x and still plus y, so a coordinate of minus x, y, and that means that sine of 180 minus theta equals y2. Apologies, I wrote a 1 back there, not a y. Therefore, sine theta equals sine 180 minus theta. Okay, here's 5 other trigonometric identities with the relationships between sine and cos for you to try out for yourself. Once you've had a go at proving them, unpause the video and we'll go through the solutions. Prove cos theta equals 360 degrees minus theta. So using that acute angle of theta, we know that this base is x, the height is y, the coordinates x, y, and so cos theta is equal to x. If I want to do 360 degrees minus theta, 360 degrees is still on the positive x-axis. However, instead of going anti-clockwise, we're going to go clockwise theta degrees. So there's my theta degrees. That means my angle all the way around the outside is 360 minus theta. Now again, what we've got is a right angle triangle. We know that the base is x. This time the height is minus y. So it's on the coordinate x minus y. And so we get cos of 360 degrees minus theta is equal to that x coordinate, which is just positive x. Therefore, cos theta is equal to cos 360 minus theta. So starting off very quickly, going through what we've already done before a few times now. So there's my radius of 1. I've got my coordinate xy because we know we've got our angle theta at the bottom there. That length of x along the base, and that length of y for the height. Now actually, I don't need a second diagram here because what I'm going to do is I'm just going to label this angle here, and that's just simply 90 minus theta. So if I form another right angle triangle from above and label the sides, so that now what I'm focusing on, and I'll do it in red, is this triangle here that we make with the y-axis. When I do cos of 90 minus theta, this angle down the bottom here, what we're going to get is that the adjacent is in fact y, and divide by the hypotenuse, which is 1. We've of course seen already that sine of theta is going to always be equal to y, so therefore we have sine theta equals cos 90 minus theta. Cos theta equals sine of 90 minus theta is almost identical. Again, starting with that point with the radius of 1, angle of theta degrees, base of x, height of y, coordinate xy. We know that cos of theta is equal to x. And so if I was to extend that, I will use the second diagram just to make it clear. If that angle's 1, if I know that this is theta down the bottom, I know this angle here is going to be 90 minus theta. Making that right angle triangle, I know that height is y and that base there is x. So when I use sine opposite over hypotenuse, what we get is sine of 90 minus theta is equal to x over 1, which is x, and therefore cos theta equals sine 90 minus theta. So let's start with a sine of minus theta. If I want a minus theta, that means to travel clockwise. Clockwise from the positive x direction, theta degrees. So we're going to go down there, creating my right angled triangle. Base is still x, but this time the height is minus y. So what we get is sine minus theta equals minus y. Of course, we know that if we have our standard acute angle triangle in the first quadrant, that coordinate is x, y, and so minus sine theta does in fact equal minus y, because sine theta is equal to y. So therefore we get sine minus theta equals minus sine theta as required. Finally, prove cos minus theta equals cos theta. Very similar to before. What we do is we start the positive x-axis, we go clockwise into the fourth quadrant. If I create that triangle, we've seen that that's got a x-coordinate of x and a y-coordinate of y, still a hypotenuse of 1, so we get x minus y. Cos of theta there, or cos of minus theta should I say, is just still equal to x, because the adjacent is still that positive x value. We've seen many times before now, hopefully you got the hang of this, x, y, just finishing it in to be complete. If I then was to use that first quadrant acute angle triangle to see what cos theta is equal to, we know cos theta is equal to x, so therefore we get cos minus theta is equal to cos theta as required. Now we move on to the binomial series. If you consider the expansion of a plus b to the power of n for some powers, we get the following results. So we get a plus b to the power of 0 is 1, a plus b to the power of 1 is a plus b, etc. And if you just go through this and expand these brackets each time, you get the following pattern. Now you should be familiar with this from A-level maths. So this shouldn't be new to you at this point in time. What we want to focus on here is really we want to focus on these coefficients. So here, the 4, 6, 4, the 3s, the 2s. And it's important, actually, we don't forget to focus on the fact that these a and b's, and a squareds, b squareds, etc., have coefficients of 1. Why do we want to focus on the coefficients? Well, if we was to look at a plus b to the power of 4, there are some simple patterns in this expansion. A to the power of 4 then decreases to a to the power of 3, decreases to a to the power of 2, decreases to a to the power of 1, and then finally decreases to a to the power of 0, which is 1, and so disappears. If we look at powers of b, initially we have b to the power of 0 as that first term on the left, which is 1, so it's not there. We then have b to the power of 1, b squared, b cubed, and b to the power of 4. So the terms a and b follow some quite simple patterns, and we could do that with any expansion. A to the power of 5, a plus b to the power of 5 would start a to the power of 5 and then decrease down to a to the power of 0, and it would start b to the power of 0 and increase and go up to b to the power of 5. What's different is these coefficients, so what we want is a nice quick way to find these coefficients. One way to try and find the coefficients is using Pascal's triangle. This is because the coefficients in those expansions actually form the entries in Pascal's triangle, for reasons we shall see in a moment. The principal property of Pascal's triangle is that actually each entry of the triangle can be calculated using the combinations formula developed in the combinatorics session. So you'll actually see that every single entry can be used calculating n choose r. The fact that we can calculate the entries of Pascal's triangle using n choose r means that we can calculate the coefficients of the binomial expansion using n choose r. As a result, it means we can write the general form of the binomial series a plus b to the power of n as a to the power of n plus n choose 1 times a to the power of n minus 1 times b, plus n choose 2, a to the power of n minus 2 to the power of b squared, and so on. So we can still see this pattern of the power of a starting at n and decreasing down to 0 by the final term. We can still see this pattern of the power of b starting at 0 and increasing until we get to the b to the power of n by the final term. And now that coefficient, which just seemed to initially to perhaps be a random number, can be calculated using n choose r. Notice that we don't do this for the first and the last term because n choose 0 is equal to n choose n, which is equal to 1. And that's because if you've got n items and you choose none of them, there's only one way that can happen. You just don't choose any. Or if you've got n items and you're going to choose n items, there's only one way that can happen. You take them all. So let's have a look at a proof of that general term of the expansion of a plus b to the n. We can prove this algebraically by showing the actual expansions, and in proof by induction, in further maths you may meet the actual proof, algebraic proof for this, but a combinatoric proof could just consider what we're actually doing. So if we was to consider that general term of the expansion, what we can do is we can think of actually a plus b to the n is equal to a plus b times a plus b times a plus b, and there's going to be n factors, all of which are the same. They're all a plus b. So here we have n factors. So focusing on the b to the power of r term, what we're going to do is from these n brackets containing a plus b, we must multiply together r b terms. And so what I'm going to do is I'm going to choose r brackets from which I'm going to multiply b. In other words, the number of ways this can be done is that we have n brackets choose r. And that gives us, I'll highlight it just to make sure we're clear on what it gives us. It gives us this part here, the n choose r. Okay, this comes from combinatorics. This is exactly the same as saying we've got a bag with 10 counters in and we want to pick 7 of those counters. How many ways can we pick 7 counters? Well, we've got 10 and we choose 7. Here we have n brackets and we want to choose r of those brackets, so we do n choose r. Now, if we consider the a to the power of n minus r terms, well, we've chosen r brackets for b. Okay, so we chose r brackets to pick b from. So that means that there's n minus r brackets left. And so the number of ways that we can choose to multiply a together, n minus r times, is we are going to pick n minus r brackets out of a total of n minus r remaining brackets. So this is n minus r choose n minus r, which we saw a moment ago. If you've got a certain amount of items and you're going to pick them all, there's only one way to do this. So what we get is, through the process of expansion, we multiply together b r times, and we can, the number of ways we can do this is choosing r brackets from n, and then we multiply together the a n minus r times, and there's only one way we can do this because the only brackets left, there's only one way to actually multiply those brackets together, and so this is how we get this general term. Example 1 says to evaluate 1 plus root 3 to the power 4 plus 1 minus root 3 to the power 4. Pause the video, have a go, and once you've done the question, press play to see the solution. So we're going to evaluate this expression. I'm going to start by just focusing on one bracket. I'm going to focus on 1 plus root 3 to the power of 4. Now, we've got a couple of ways that we can calculate the coefficients. I can use Pascal's triangle, or I can use n choose r. In this case, because we've got such a small amount of terms, I'm going to use Pascal's triangle. So I want to expand and find Pascal's triangle up to the row which contains the number 4 in its second term. So there we have the fourth row. So now I know the coefficients of this expansion. I know there's going to be 4 terms. So what we do is we say equals, and I just use those patterns from the series itself. We're going to start with a, which in this case is 1. So we start with 1 to the power of 4. And we always start with that 1 to the power of 4. We'd do root 3 to the power of 0, which is 1, so we don't bother. We move on a term. I use the coefficient of 4. I then do times 1 to the power of 3, because I decrease that power by 1. And each term I move along, that power of 1 is going to decrease. Now the power of root 3 is going to increase, and it's going to be root 3 to the power of 1. Moving along, coefficient is 6. We're going to get 1 squared, because we're going to decrease the power. This time we're going to increase the power of root 3, so we get root 3 squared. Running out of space, so I'm just going to put a plus dot 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 and continue underneath. So the next term has a coefficient of 4, and we're going to decrease the power of 1, so it's 1 to the power of 1. And I'm going to increase the power of root 3 to cubed. And finally we get to the last term. So the coefficient's 1, I'm not going to bother writing it. We're going to do a to the power of 0, which is 1 to the power of 0, which is 1, so I'm not going to bother writing it. And I just get left with then root 3, and increasing the power, we get power of 4. And there's a quick check I can do here as well. If I've done the a and b terms correctly, their powers will add up to 4 each time. So in the first term we just got 4. Second term I've got 3 plus 1. Third term I've got 2 plus 2. Fourth term I've got 1 plus 3. And final term I've got 4. So I know I've done things correctly. So let's tidy this up and see what we get. So 1 to the power of 4 is 4. I then get 4. I can ignore the 1 cubed because it's just 1. So I get 4 root 3. Plus 6 times 1 squared is just 6. Root 3 squared. Root 3 squared is just 3. So I'm going to get 6 times 3. Moving on to my next term, I get 4 times 1, which is 4. A nice way of doing root 3 cubed is to take the root 3 squared from the last one, which is 3, and multiply it by root 3. And that will save you a little bit of time. And then finally we come on to the fourth term. And what we're going to do is I'm going to get root 3 to the power of 4. And again, what I can do now is I can multiply root 3 cubed, which was 3 root 3, by root 3. So I get 3 times root 3 squared, which tally up. Now I'm almost there. Seems like a lot of algebra initially, but hopefully we won't have to do so much in a moment. First two terms are unchanged. I then get plus 18. 4 times 3 is 12, root 3, and then 3 times 3 is plus 9. Now you may be tempted to actually tidy this up at this point, but we've got to remember that we've got another bracket to expand. And the easiest way to deal with this confidently without making any silly mistakes is to actually just take that bracket and deal with that now. So we're going to say 1 minus root 3 to the power of 4. Now the only difference between these two brackets is that the b term is negative. So what that means is every term in my expansion where the b term, or root 3, is to an odd power, is going to become negative. So the first term's positive because 0. It's neither odd nor even technically, but we're calling it an even for argument's sake in this case. The second term, we have root 3 to the power of 1. So this is going to be a negative term. So we get minus. And when we expand it out, we're going to get exactly the same. It's just that it's negative. The third term, we had root 3 squared, so it's positive. The fourth term, we have root 3 to the power of 3. so it's negative. Again, each time these terms are going to be exactly the same. And then finally, the last term, the power is even, so we get a positive number, so we get plus 9. And so what we can do is we can actually now evaluate 1 plus root 3 to the power of 4 plus 1 minus root 3 to the power of 4 as 1 plus 1, which is 2. The 4 root 3's cancel out. 18 plus 18 is 36. The 12 root 3's cancel out. And 9 plus 9 is 18. If I add that all together, it evaluates and gives us an answer of 56. Here we have the definition of the binomial series, which is a special case of the binomial expansion. We'll define it as 1 plus x to the power of n is equal to 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n times n minus 1 times n minus 2 over 3 factorial times x cubed plus, and the pattern goes on. Now this series is valid for any rational n if and only if the modulus of x is less than 1. So what we're talking about here, any rational n, is whole numbers, so integers, positive or negative, and fractions. Okay, so any rational number, we can do this expansion. A couple of things to note is that this expansion is infinite, is an infinite series. And another important thing to note is that if we just modify this definition ever so slightly and say, okay, let's put n over 1 factorial, we get more of a pattern. Notice that we start with 1, and it's 1 times x to the power of 0 if you want to be technical about it. We then get x to the power of 1, x squared, x cubed. So the powers of x ascend in increments of 1 each term. So what I mean by that is the power increases by 1 each term. And then we get this coefficient, and that coefficient is defined in a pattern as well. So our first term, x to the power of 1, the coefficient is defined as n over 1 factorial, or n over 1. For the second term, I get n times n minus 1 over 1 times 2. For the third term, I get n times n minus 1 times n minus 2 over 3 factorial, which is 1 times 2 times 3. So what we get as the coefficient is a fraction where the number of terms in the numerator and denominator are equal to the power of x. In the denominator, we're always going to write a factorial involving integers. We're starting from 1 and counting up to the power of x. In the numerator, we start at n and we count down from n the number of terms that we have in the denominator. So the first term we just had n. Second term we've got 2 terms, so we do n minus 1. Third term we've got 3 terms, so we do n minus 1, n minus 2. Learning the pattern means that you don't have to learn the formula. The pattern's far simpler to use. Example 2 says expand 1 plus x over 2 to the power of minus 6 in ascending powers of x up to and including the x cubed term. And it says to state the values for x for which the expansion is valid. Have a go at doing this expansion. Pause the video while you're doing so, and then when you're ready, press play to see the answer. Okay, so I'm going to start this question by first of all stating the values of x for which the expansion is valid. Quite often because I forget to do that because it's the last part, and I have relief when I've done the question, I forget all about the last part. So let's start with that. What we know is the definition is that whatever's in that x position must have a modulus of less than 1. So what we mean here is that modulus of x over 2 must be less than 1. Now if I multiply both sides by 2, what I get is that the modulus of x must be less than 2. If you're not 100% sure what we mean by that, helps first of all if I write the number 2, but what this means is that x is actually a value that lies between negative 2 and positive 2. Okay, so let's have a look at the expansion. The expansion I tend to do in about 3 lines. So we have 1 plus x over 2 to the power of minus 6. Using the pattern, it always starts 1 plus. We're going to have x to the power of 1, so what that means is we're going to be having in the denominator one term, 1 times nothing else. In the numerator, we're going to count back from n. N is 6, so that's minus 6. And then we get just multiplied by x, which is x over 2. Second term is going to be x squared. So in the denominator, I'm going to have 1 times 2, because we're going to have 2 terms. In the numerator, I'm going to have to count down from minus 6. So I get 2 terms. So minus 6. Careful, don't rush in like I have. This will go down. And remember, it goes down from minus 6 to minus 7. Make sure that 2 is clear. And then I get x over 2 squared. And actually, once you get the first term and the second term, the rest, it starts to flow a little bit more. So x cubed, we're going to multiply. So we get 1 times 2 times 3 in the denominator. We're then going to count down from minus 6, 3 terms. So we get minus 7, minus 8 in the numerator. And then I get x over 2 cubed. And I'm just going to put plus dot, 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 because it's an infinite series and we're just focusing on the first 3 terms. So, starting to work on this and tidy it up. 1 plus is nice and simple, except in this case, when I come to tidy up this, I get minus 6 over 2 gives me actually minus 3x. So we need to edit that and say, okay, that's minus 3x. Second term, I get minus 6 times minus 7 over 2. So 2 negatives multiplied together, it's going to be positive. Great. I cancel a factor of 2 with the 6, so I get 3. Minus 3 times minus 7 is plus 21. Square the x term means I've got to square the x and I've got to square the denominator too, so I get over x squared over 4. Coming to my third term, I've got 3 negative numbers multiplied together, so that's going to give me a negative. And in a denominator, I get 1 times 2 times 3, which is 6, so I'm just going to cross off the minus 6. And so I get 7 times 8, so I get minus 56, and then I get x over 2 cubed, which gives me x cubed, remembering to cube the denominator. Now notice how I'm using brackets here to help me. Once I've squared or cubed those terms, I've brought the squared or the cubed inside the bracket so that I know that I've dealt with that denominator. And I do exactly the same when I'm dealing with coefficients. Tidying up now, because I should now be able to get to my final answer. 1 plus x over 2 to the minus 6. I get 1 minus 3x. Nothing changes on that term. Can't really do anything with the next term. All I'm going to do is write it as a fraction in the coefficient. So I get 21 over 4 x squared. And then minus 56 divided by 8 will give me minus 7 x cubed. Must remember the plus dot, 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 dots on the end. And there is our expansion. Take your time, it will come with practice. Use the patterns to help you do the expansion. It's far simpler than learning that formula. And just follow the patterns, take time, don't rush the evaluation of terms. Break it down into nice clear steps where you get a routine of what you do in each step. For me, in the first step, I just write out the expansion. In the second step, I tidy up the coefficient and the x term individually. And in the third step, I then tidy up that coefficient and x term together. Example 3 says expand 1 over the square root of 1 minus 2x in ascending powers of x up to and including the term in x squared. Hence, by writing x equals 1/8 in your expansion, find an approximate value for root 3 in the form a over b, where a and b are integers whose values are to be found. Pause the video, have a go at the question, and when you're ready, press play to see the solution. So we're going to expand 1 over the square root of 1 minus 2x. This might be a little bit confusing at first, but if we think about this, this is just 1 over 1 minus 2x equals there's a square root in there, 1 over 1 minus 2x to the power of a half, which in that case is 1 over, it's not even 1 over, because what I want to do is I want to use negative indices here. This is 1 minus 2x to the minus a half. So what I want to do is I want to expand 1 minus 2x to the power of minus a half. And we're just going to go up to the x squared term. So let's have a go at that. 1 minus 2x to the power of minus a half equals, start with 1 plus n, which is minus a half, I'm going to divide that by 1 because this is the x term, and the x term is just minus 2x. Go on to our x squared term. We're going to get 2 terms, so in a denominator we're going to get 1 times 2. In a numerator I'm going to count back from minus a half, so just be careful. Minus a half and then minus 3 over 2. Working with fractions is far easier than working with decimals here. And then I get minus 2x squared. Okay, so let's tidy this up a little bit. The first term, I get minus a half divided by 1. We've got 2 negatives there, so it's still going to be a positive. So we're going to get 1 plus. Half divided by 1 is just a half, and a half times 2 is 1. So we get 1 plus x. Moving on to my next term, I get we get minus a half times minus 3 over 2 is positive. The minus 2 is going to be squared, so that's positive. So we're going to get another positive term. If I have 1 half times 3 halves, I get 3 over 4. Divide that by 2 again, I get 3 over 8. And we multiply this by minus 2x squared. Squared of minus 2, I get 4. Square the x, I get x squared. And so finally, I get 1 minus 2x to the minus a half equals 1 plus x plus 3 over 2x squared. So cancelling the factor of 4 in the numerator and the denominator, we get 3 over 2. Okay, so there's our expansion. Technically I should have plus dot dot dots at the end, so I'll do that. It then says, hence by writing 1/8 in your expansion, find an approximate value for root 3 in the form a over b, where a and b are integers whose values are to be found. So I could start initially by saying, okay, x equals 1/8. If I deal with the right hand side, and I'm going to label the right hand side, I get right hand side equals 1 plus 1/8 plus 3 over 2 times 1/8 squared. So if I evaluate that, I get 1 plus 1/8 is 9/8. And then I get 3 over 2 times 1 over 64. So in the numerator, I get 3. In the denominator, I get 64 times 2, which is 128. And then tidying up, 16 times 8 gives me 128. So I get 16 times 9, 144 plus 3 over 128. So on the right hand side, this evaluates to give us 147 over 128. Okay, what I've also got to do is I've got to evaluate the left hand side. So the left hand side, easiest way to do this is to start off with the original definition. Gives me 1 over the square root of 1 minus, so tie that up a bit, 1 minus 2 times an eighth. Well, 2 times an eighth is a quarter, so 1 minus a quarter is 3/4, and I get 1 over the square root of 3/4. Or we can have 1 over square root of 3 over the square root of 4. Now, because we've got 1 over that, I can flip the fraction and write this as root 4 over root 3. It's really important you're able to manipulate your fractions easily and confidently. Square root of 4, of course, is 2, so I get 2 root 3. Now, if I put the left-hand side equal to the right-hand side, what we get is 2 root 3 is equal to 147 over 128. So I'm going to times by the root 3, and I'm also going to times by 128 over 147, so that inverse fraction, so that I can make root 3 the subject. And so what we get is that root 3 is equal to 2 times 128 over 147. So root 3 is in fact 256 over 147 approximately. Now if you do this on your calculator, just to get a decimal value, to get an idea of this, this approximation actually gives us a value of 1.741. And if you actually do root 3 on your calculator, it's equal to 1.732. So it's not a bad approximation.